Afternoon, everybody. We're just about to start our webinar on a review of different kind of process safety testing options available. Good afternoon from the UK, where we're presenting from, but we're giving this talk for our Sigma-HSE US branch. So good morning to anyone attending over there. We're just going to hold on a couple more minutes for some more people to turn up, and we'll dig into the talk at that point. Okay, so hello everybody again. Thanks for joining our talk today, covering a review of process safety testing options. We're going to be covering a range of tests that are available for studying both reactive and non-reactive systems, and we'll go in a little bit on the differences between those from a process safety perspective. So we're presenting from our laboratory and office in Winchester in the UK. It's myself, Dr. Ollie Armstrong, and Luke Bucktrout from the Chemical Process Evaluation Laboratory at Sigma-HSE. And there's a picture there of the two of us in the lab at the bottom left. So yeah, we've promoted this talk in the US as well. So good morning to those of you over there. It's good to see some familiar names on the attendance list. So hello to you, and also to some new people joining us for the first time. So a bit of an overview of what we'd like to cover today, initially laying out what exactly we think is a process failure from a process safety standpoint, not really considering quality issues and so on, which is more for the client's consideration. Secondly, to do with process failure and process safety, why might analysis of both the normal process, the desired operation, and misoperation be required, and the importance of considering both of these scenarios. Thirdly, when testing might be needed or when it's most appropriate to start testing. And then finally, this will be the largest section that we'll cover through, myself and Luke, which tools are available, mostly on the testing side, but we'll cover a little bit on the kind of appropriate assessments that may be used to infer appropriate tests also. So yeah, from that overview, our objectives are that hopefully people will have learned somewhat a little bit more about process safety, both the potential consequences, importance, and why controls need to be put in place. Majorly on the testing routes available, that's the bulk of the talk that we'll be going through today. Again, some assessment options and risk assessments and so on. But also we'd like to educate a little bit on not too much detail on the tests themselves, but hopefully we explain a little bit on how these tests may be appropriate or relevant to your processes. So just a little bit here on Sigma-HSE. We've got a range of laboratory tests available covering different niche areas, and we will be covering all of these topics today. So chemical reaction hazards testing, reactive systems testing, thermal stability. There's different ways of approaching this also for different applications. Powder, dust, fire and explosion parameters testing. Similar to that, gas and vapors flammability testing, and also tying into those electrostatics properties testing. So on the got a nice video there on the right hand side of a gas and vapor test that is studying the LEL UEL parameter, which is lower explosible limit, upper explosible limit, and we have typical orange and blue flames being indicative of either the lower limit and the upper limit. And as we said, there's a wide variety of different assessments that can be performed to ensure that your processes are operating safely. A lot of these can be done in-house or with the help of consultants. And again, the choice of which assessments to use really needs to keep in mind the scale and the risks inherent in a process. And the greater risk present in a process, then the more detailed assessment should be used to consider every potential eventuality and potential misoperations, as we suggested earlier. Some of these assessments will need to be tailored to any local regulations. So we're quite used to talking about regulations in the European Union. Obviously, there's other local regulations for the Americas, Asia, and so on. So into the topic of the talk, what we consider to be process failure, what is it? So for reactive systems, many desired chemical reaction processes, so these are the operations that people want to perform on plant, can have an inherent risk of exothermic reactions themselves, and then unwanted potential decomposition reactions, which can also be exothermic. So yeah, these secondary decompositions often are exothermic and can quite often produce gaseous products also. So this combination really of exothermic energy, which if not managed properly can lead to temperature increases of the system, alongside permanent gas generation or vapor generation, really have the highest risk potential for any kind of confined system, vessel, or reactor. So unfortunately, due to these kind of risks, runaway reactions have caused a number of industrial incidents over the years, either in reactive systems or unreactive, and we will go through a couple of examples of those in the next couple of slides. So those first few bullet points are mostly talking about reactive systems. Obviously, there is also a risk of explosion or fires in what we term non-reactive systems, where these materials may not have a desired reaction as part of the process, but they can form flammable atmospheres, and where there isn't sufficient controls in place to handle those materials safely or appropriately, then process failure can occur. So just to rush through a couple of examples of where process failure has occurred, starting with reactive systems. With Bhopal in India was a very famous example of a chemical reactor explosion. Some maintenance washing processes where either equipment and controls weren't sufficiently in place alongside sort of operator and process failure on that level led to incompatible materials mixing, leading to thermal runaway, and unfortunately many deaths in that case. Bringing it up to more recent years, in 2021 in Europe, this was not a desired reaction, it was a solvent waste tank explosion, but again there was a failure of process control in that materials going into the waste tank weren't disclosed properly. There was a runaway reaction inadvertently that led to increased temperature, pressure, and explosion. And to non-reactive systems, we did have an example of one in the US that occurred recently. That must be on another slide. So in Nebraska in 2025 in July, there was a biofuels plant explosion, very similar to the example on the left-hand side where there was wood dust present. So it's a very benign material that people understand or think they understand. But when people are very used to a material, that can sometimes lead to not fully assessing the risk that is actually inherent to these forming a flammable atmosphere. Same on the right-hand side, materials used in bakery products, again, causing fires, secondary explosions. And even if there is not deaths occurring from these events, there can be capital damage to infrastructure, potentially job losses, closure sites, company closures, and so on. So in our second chapter, why it is important for analysis of both the normal process and misoperation. So firstly, understanding how something is going to occur in the normal process. It is very important to understand the material being used fully. So there are certain parameters such as ignition sensitivity, sorry, we're having some trouble with the slides. So even though a material, if we know that a material is going to be present and forming a flammable atmosphere in our desired operations, then we need to understand the sensitivity to ignition so that we can put any potential controls in place to try and prevent that initial ignition. Also, explosion severity limits, so that if this is really designing for a worst case, that if an explosion occurs, that any generated pressure can be diverted safely away from staff, population nearby, from expensive plant within the facility. Additionally, thermal stability. If any materials are going to be intentionally heated up, then we should know what is the safe limit to actually heat these materials to without causing decomposition. And then in reactive systems, if we're going to mix certain reagents together, we should have full understanding on the reaction enthalpies that will occur, and additionally any potential for pressure generation, again by vapor pressure or production of gas byproducts or products. And then finally to that point is electrostatic properties, which can either validate control measures in place, such as static dissipative PPE or flooring, but also to understand the electrostatic properties of the materials in use and how this might tie into ignition sensitivity tests. And then the second section really tailored more to misoperation, what happens in your process if something goes wrong. Again, inadvertent heating, thermal stability links to that in understanding how it might behave at elevated temperatures. Reactive systems, runaway reaction potential, but this is really additive to the first points that are studied. Again, in a worst case scenario, understanding your ignition sensitivity, explosion severity, explosivity limits, these really feed into understanding what may occur in a worst case scenario as well. So of course, we think it's important. Why is analysis of these scenarios required? Of course, it's very good from a process safety standpoint to understand these, but there are additional regulations that will enforce you to understand these. So it's not just about optimizing your process and ensuring you do it most productively and profitable, but also there are regulations in place to protect the health of citizens and employees. So to that point as well, identification of the worst case. This is very important to know really what tests are best chosen by using various assessments and trying to infer of all the scenarios of things that might go wrong, which one is going to result in the worst case scenario and is most likely to cause a potential explosion, for example, and therefore we need to design to this case to have a solid basis of safety. So to add to that as well, once we know the worst case scenario, we know what material or reaction mass we are looking at, what is going to happen to it, what happens if a flammable atmosphere does explode at its optimum parameters, what does happen if a reactive mixture is allowed to go along the route of thermal runaway. At that point, we need pressure relief systems when you have confinement of that system. And there are various physical parameters that are key to really ensuring that you can handle the amount of mass and energy that needs to be removed from that system. So even if the worst case does occur, it can still, using these relief sizing techniques, you can still maintain the integrity of your plant and not cause harm to your operators and such. So thirdly, when we might suggest testing to be needed, this is a kind of typical timeline for suggested testing for reactive systems. So going through an R&D process for designing a new chemical product, going through R&D to scale up and then production. So in early stages, knowing which kind of molecules that we want to produce, we can use literature, we can use simulations and calculations to identify any potential reactive hazards. And at this point, when we've got lots of candidate molecules, you can make a choice to avoid certain ones that may be high risk. That kind of leads in quickly to thermal screening testing. So these tests can be typified by high throughput, where you can test lots of samples very quickly. So again, this is good for early stage development. Again, screening out the riskiest candidates. This goes hand in hand with starting to look at reaction calorimetry, so understanding the desired reaction that's going to be performed on plant, and again, matching this up against the thermal stability screening data to see whether there's any real risk of the desired reaction, if you have a cooling failure, for example, triggering a secondary decomposition, and being cognizant really of whether there's any potential for thermal runaway to occur with that system. So when we start getting some of that data with the thermal screening, the reaction calorimetry, we can start looking at small scale hazard assessments and feeding those into design and controls for pilot plant scale production, starting to scale up. And then the final kind of area of testing at this point would be some adiabatic calorimetry, used to really precisely investigate reaction enthalpies of decomposition or reaction enthalpies, pressure rise rates, temperature rise rates for relief system design, and having much more certainty around the controls required in place to ensure that your desired process can come off without a hitch really when going to production scale. So finally getting into the testing section now, which tools are available. Again, we've kind of highlighted there's lots of things to consider when designing a new process or just making changes to an existing process. And there really are a lot of different tests out there with niche applications, and really selecting the correct one for the correct application is very important to make sure it's used properly and relevant. So we're going to start with the dust powder explosion sort of testing. So we have a explosion pentagon on the right hand side. These 5 key components need to be fulfilled for an explosion to occur in the case of a dust explosion. So we have a combustible dust at the bottom of the pentagon. This flammable material needs to be here to act as a fuel. Next up, we have ignition source. So there needs to be a sufficiently energetic ignition source to ignite that material. For a dust explosion, we need a dispersion of these dust particles to be present. So not just a layer or bulk of material, but it for actually to be kicked up into a cloud of some sort. On the bottom left side, we've got oxygen and air. So for any kind of combustion mechanism, we need oxygen to be present. And then finally, for an explosion, rather than just a fire, rather, we need confinement of that dust cloud within the system. So for dust cloud explosions, the material parameters of the material being tested or present in the process really is key to both the ignition sensitivity and potential explosion severity. So when you're sending material for testing, the chemical composition of the material sent for testing should be in the same form as that will be used on plant. So thinking about purity or any potential presence of inerting agents that may be added before or after testing, this really will have or can potentially have a large bearing on the results, and may not give a true picture of how it might react on plant. Particle size really is a key parameter for dust explosivity. Again, it should be representative of a worst case that might occur in your process. Yeah, the form of the sample, so whether it's chemically pure, a mixture of different components, or a blend that's kind of stuck together, should also inform on how the material should be prepared before tested, because that can give a false negative result or a false low result. Moisture content also is very important, and it's reasonable to consider a worst case where the material is in quite a dry state. When we're talking about fine powdered or dust materials, it's typically very easy for them to become dry around hot motors or exposed to sunlight and so on. So it's a very reasonable scenario to test it dry. Additionally, the particle morphology and surface area can impact on the sensitivity and severity, but generally less so than the particle size relationship. And again, this should be focused on a reasonable worst case scenario so that you're prepared for that worst case eventuality. So we just have some simple plots here to sort of demonstrate that particle size relationship with ignition sensitivity and severity. So the top two graphs, we have a minimum ignition energy values on the y-axis and particle size of that tested on the x-axis. And we can see that for these examples, and this is typical of materials, that as the particle size reduces, the minimum ignition energy required to ignite that material as a dust cloud also reduces. And it's quite a steep downward trend. It does tend to have a break point at some point. So with the prevalence or the more common occurrence of nanoparticles now, that trend seems to break and slow down when we're getting to a really small scale. Additionally, the plot on the bottom, on the y-axis, we have a measure of explosion severity, KST. Same again with particle size on the x-axis, and we can see that for all of these wood powder samples, a reduction in particle size leads to an increase in explosion severity. So there are various tests available for dust combustibility or explosibility, and they tend to explore either 1, 2, 3, or all of the parameters in that explosion pentagon, so that appropriate controls can be put in place to handle the materials. Firstly, we can establish whether the material or dust is actually classed as being combustible, and it can be screened in the Hartmann tube, or the decision rule is taken to a 20-litre or 1-metre cube sphere. When we know the material is classed as combustible, then we should look at the sensitivity and severity tests. So we can test for minimum ignition energy, what is the lowest millijoule energy that can actually ignite the material as a dust cloud. The MIT, so this is like an auto ignition temperature, again with the material as a cloud. Layer ignition temperature is a little different, that we're testing the material as a layer, as a bulk. Lower explosible limit or minimum explosible concentration in the US. This is looking at what is the weakest concentration of the dust clouds that will actually support combustion, because if it's too dispersed and too low a concentration, there won't be propagation of any ignition of the material. And then finally, for sensitivity, is the limiting oxygen concentration. So some clients may go with a control of using inerting of a process with nitrogen or argon to control any explosion risks. So we can see the break point at which how much inerting you need to do of your system to prevent an explosion occurring. Explosion severity, Pmax KST, combines all 5 parameters of the explosion pentagon to find what might be the maximum explosion that can occur. Burning behavior and burning rate, again, these are slightly different. Rather than looking at a dust cloud, looking at more at the material in bulk and its combustible behavior or nature. So just to illustrate some of these tests and how they correlate to the explosion pentagon as discussed, we have the minimum ignition energy on the left-hand side, looking at a dispersed dust cloud. We have the combustible material present, and we vary the ignition source energy to find the limit. Moving next to that, we have the layer ignition temperature, where we have a layer of material on a hot plate. So at that point, we're only studying the presence of the combustible fuel and the ignition source being the elevated temperature, and what point does it stop igniting the material. Next to that, MIT cloud. So again, we have a dispersion of a dust cloud, the ignition source as elevated temperature, and the combustible dust powder as the fuel. And then finally, on the right-hand side, we have a 20-litre apparatus, which we use for dust combustibility, LOC, MEC, and explosion severity. So as you can see in the pentagon, for explosion severity, we're looking really at the optimum conditions. What is the maximum explosion power that we can produce with that material? So just to give a bit of an idea how these tests might apply to various unit operations. So minimum ignition energy, this is typically looking at electrostatics issues as an ignition source. So we can imagine that if we're moving a insulating material through any kind of process, there is potential for electrostatic charge to build up here and discharge, which may potentially ignite the material itself. So all of these unit operations that involve moving a material, MIE would be suggested to start with. Thermal stability for silos, storage, size reduction, milling, ovens and dryers. We either have intentional heating in these unit of operations or inadvertent heating. If we take size reduction, maybe we have a bearing failure, which can cause an increase in temperature. So we should know what is any potential risk thermal stability wise for decompositions to occur. Same goes for size reduction, milling, ovens and dryers. It's useful to test for minimum ignition temperatures, both as a cloud and layer, because we might have hot motors present, metal on metal glancing, which can cause hot sparks to be present. So we move through now to electrostatics, and we just have a good kind of summary table up on the screen now for the various kind of electrostatic discharges that may occur in industrial settings, their typical kind of ignition energy range. So we can relate that back to the minimum ignition energy testing to see whether or not it's likely to ignite our material. And we have ignition risks on the right-hand side. So the lowest kind of typical discharges, such as brush discharge, up to about 3.6 millijoule. this is only really typically a risk to gases and vapors, which have a lower MIE, but not typically to dust clouds. We do get dust combustible materials that may have a sensitivity in the single digits millijoules, but it's quite rare. So there are various tests for exploring electrostatic properties. So these three we have here are for looking at bulk powder materials. On the left-hand side, we have the charge relaxation or decay time test. So if we know we have an insulating material that can generate a charge through movement or otherwise, how long does it take that material to give up its charge and become neutral? So this can be a risk if you're moving a material into an IBC or some other storage vessel. How long is it going to sit in there charged, and therefore a risk of generating an electrostatic discharge? So yeah, as a fast decay, if a material has a fast decay, then it's typically a lower risk. We also have powder volume resistivity. So this is for asserting whether the material as a bulk is going to behave as an insulator, or it's kind of the related term to resistivity. Materials that we might expect to be conductive as a solid bulk material, graphite, for example, when it's in a powdered form and it's allowed to pack naturally, it may still register with a resistivity value or a higher resistivity value than would be expected for the material. And that's just due to how the powder actually packs within the cell and the air spaces between individual particles. Chargeability on the right-hand side is basically just simulating a movement operation of a material through stainless steel pipe or whatever is appropriate to the actual process. And it just provides indicative results on any potential accumulation of charge in a material and the polarity of that charge. There are also electrostatic tests for looking at surfaces or solids, such as floor resistivity testing. Again, this is kind of validating efficacy of controls that might be put in place to prevent electrostatic discharge. And they can validate either new installed floors or also to check the continued working of old installations. Charge transfer testing can be used to measure brush discharge potential from isolated surface to conductors. So we can measure the functionality of certain overalls, PPE, and so on that operators might have to wear, and what kind of discharges this kind of clothing may give off. On the right-hand side, finally, we have surface and volume resistivity. And again, similar to the floor resistivity, this is looking at resistivity through a plane or through a bulk of a solid material to assess efficacy of static dissipative materials, coatings, enclosures to check that they're working as they should be. Finally, on electrostatics testing, not to forget liquids. We've talked a lot today about solids, but liquid conductivity can also be measured. So typically, organic liquids can be insulating. So they can also accumulate a charge through movement or other charging mechanism, which presents a static ignition source risk. Obviously, thinking about organic liquids, there is a high risk potential here as volatile vapors generally have low ignition sensitivity values. So any kind of electrostatic discharge in this system is quite high risk. So that is myself finished for these sections. I'll hand over to my colleague Luke now for the next sections on testing.
Thank you, Ollie. I just want to apologise for the technical difficulties. That was my fault. Hopefully we don't have any more of those. So now we'll move on to the gases and vapours testing. They're similar to dust in the fact that they can also form explosive atmospheres, and the criteria for this explosivity is broadly the same. We can see here we have this explosive pentagon again. Oxygen and an ignition source is still required to form an explosion, but now we're concerned about the dispersion and confinement of a gas or vapor instead of a dust. Starting off then, we have flashpoint testing. So there's typically two variations of this test. We have the closed and open variations, and it's usually the closed cup apparatus which is preferred because it tends to give a bit more of a conservative value. We also have the few tests for flammability, sensitivity, and explosion severity that are quite similar to the ones that we do use for the dusts. So again, we have minimum ignition energy, which is directly comparable to the dust testing version. Although, as Ollie briefly mentioned, the MIE of gas and vapors is usually very low. So quantifying this is not normally too useful when trying to design controls around it, because there's not much control you can do with those low levels of MIE. We also have auto ignition temperature, which works very similarly to the minimum ignition temperature for the dust testing. And then we have the lower and upper explosible limits, which again, very similar to the minimal explosible concentration test that we use for the dusts, where we're exploring the upper and lower limits of flammability with respect to concentration. And again, in terms of explosion severity, we're trying to find the optimum conditions which produce the largest pressure rise, and again, we'll get values for the severity of that explosion, kg. So here we can see photos of some of these tests. Starting from the left, we can see the auto ignition temperature equipment, whereby you inject a known volume of sample into a round bottom flask situated within an oven. The sample will vaporize, and if the temperature of the oven is hot enough, the vapor will then ignite, and we can see that here. It's not always this violent. Quite a lot of the time when you're at those sort of boundaries between it igniting and it not igniting, we'll just get a small flash in the bottom of the flask, and we can observe that with the mirror that's situated on top. Next to that, we have the LEL-UEL. You'll recognize that photo from the beginning of the slide. This test consists of a larger 5 to 20 litre flask, which can be made of glass or steel, and we put that flask in an oven whereby a gaseous sample is added, or if a liquid sample is added, we would then vaporize that under vacuum at a set temperature. We then provide a set energy by these two electrodes that you can see in the middle, and we try to ignite that atmosphere to try and investigate the flammability limits with respect to the concentration. Moving along then, we can see the closed cup flashpoint apparatus. In this test, we're trying to determine at what temperature a liquid forms a flammable vapor. So in this variation, we typically ramp the temperature of the sample at approximately 6 degrees a minute. We do this under stirring, and at every degree increment, we stop the stirring and dip in a pilot flame to try and ignite that headspace. And lastly, again, we have that familiar 20 litre vessel. In this case, it's designed to investigate the maximum pressure and explosion severity values for gases rather than dusts. So here we can see how these values sort of link together in this graph. So starting from the flash point, which sits quite tightly to the vapor pressure curve, since the test itself investigates the minimum temperature at which the liquid forms a flammable headspace, we can then move up in temperature from this point, where we can see the lower flammability limit, which gradually decreases with increasing temperature. Opposing this, we can see the contrasting trend for the upper flammability limit. So whilst the LEL-UEL testing is concerned with finding the flammability limits of a gas or vapor, we can see that the auto ignition temperature investigates the optimum concentration and temperature. So again, it's that worst case scenario there, where all the conditions are perfect to form that ignition. So we're now going to move on to the testing available for more reactive systems and investigate the hazards associated with the running of reactions. So it's first important to understand the potential causes of these hazards, the most common of which we can see here on this slide. So firstly, we have the improper assessment of scale-up differences, and that can be due to not having the appropriate data to determine your heating or cooling requirements at process scale. It can also be due to improper reactor design. As we said before, you want to account for the worst case scenario, and occasionally this isn't taken into account. Next, we have systems failure. So that can be anything ranging from complete power loss and shutdown to things like agitator failure, leading to accumulation of reagents, line blockages and things like that. We then have process failure, which can arise due to operator error, mischarges, incorrect temperatures, even cleaning, like we mentioned earlier. So the key hazard that arises from these scenarios is pressure. Rarely will exothermic energy and temperature be a hazard on its own. It's the pressure which can rupture these reactors and cause the big explosions. Now, clearly, temperature and pressure are linked. High temperatures lead to higher vapor pressures, and then those high temperatures have the potential to trigger the secondary reactions and decompositions. Both of those can potentially generate permanent gas, and this pressure generation is on top of any usual gas generated from the reaction. It's important to note that we can utilize this pressure temperature relationship to try and control the temperature of a reaction through something called tempering. And a system can be designed whereby any build-up in vapor pressure outside of normal operating conditions can be vented from the reactor to remove the heat from the system and prevent us from getting into territories where we're, accessing temperatures that can cause these secondary reactions and decompositions. So just to highlight again why pressure is so paramount in chemical reaction hazard analysis, we can look at this simple example whereby we supply energy to hydrogen peroxide to yield the decomposition products water and oxygen. So we can see here that the volume of each constituent takes up these volumes at atmospheric pressure. And if we were to confine this reaction to, say, a 1 litre vessel, initially at standard temperatures and pressures, the resultant pressure post-reaction would be approximately 362 psi. So you can see how that can be quite a dangerous hazard if not accounted for. So how do we apply this data then? So if we look at this diagram, we can see how a typical isothermal process might look under normal conditions if we follow this dashed line. But in order to design a safe process, it's important to simulate that worst case scenario. So in this case, we have cooling failure, and with certain CRH test methods that I can delve into later on, we're able to determine the total enthalpy of the reaction. And it's this value that we can use to calculate the adiabatic temperature rise, which then allows us to determine the maximum temperature of the synthesis reaction, the MTSR. We can then assess if this MTSR has a potential to trigger any secondary reactions, any decompositions, which can then lead to thermal runaway and that pressure generation that we talked about. So once we've obtained relevant data, we're then able to assign criticality classes by combining the 4 temperature levels. So we have the process temperature down here, the MTSR, and the maximum technical temperature. So that's the temperature at which your solvent system starts to boil. We then have the temperature at which the time to maximum rate for that decomposition is 24 hours. So it's abbreviated to TD24 here. And you can see how that's presented here in this graph by these grey boxes with the zigzag line. So for class 1, we can see that the technical limit cannot be reached and the decomposition reaction is not critical since the MTSR is below the TD24 value. So only in worst case scenarios where inadvertent heating is applied can the technical temperature be reached. But even at this point, the evaporator cooling serves as an additional safety barrier. Class 2 is similar. However, as you can see, the boiling of the solvents is equal or greater than the temperature of decomposition, which means in the case of inadvertent heating, we don't have access to that safety barrier of tempering the reaction. So for these two classes, if heat accumulation can be avoided, no special measure is required. Moving on then, we have the class 3, where the technical limit is reached, but the decomposition reaction is not critical. So boiling of the solvent will increase the reactive pressure, and this can be used to temper the reaction as a first sort of measure. Because we're reaching this technical temperature, we will need alternative discharge systems to be designed in this case. This can be, for example, pressure relief valves that can vent off the solvent vapor to temper the reaction mass. But then further downstream, you're going to need to treat that discharge and effluent, especially if it's two-phase flow that's coming out of the reactor. Class 4 then, quite similar to class 3, but has one major difference really. It means if the technical measures fail, the secondary reaction will be triggered. So any emergency relief systems must be designed with this additional heat release in mind. Again, you're trying to encompass that worst case scenario. And then criticality class 5, that is the worst class, and to be honest, it should just be avoided as much as possible, and you should really look at redesigning your reaction to avoid this. So how do we get this data? First, we have to determine the type of testing your process needs. So CRH testing is not an off-the-shelf product. You have to take the time to discuss the process and tailor the testing proposal to your needs and requirements. So what we do at Sigma-HSE, to make sure that you're completely clear on what we recommend and why, we would generally go through a test program proposal like this one, where we usually recommend thermal screening of any raw materials, any of the reaction mixtures and intermediates, and then we can start to map out what other testing is suited to your goals, whether that be reaction calorimetry, adiabatic calorimetry, worst case scenario simulation, or vent sizing. So we'll talk a little bit about that now. Starting off then with the screening thermal stability tests. They're usually characterized by low sample requirements, which is especially good for novel materials where the sample amount is quite limited. But it's important to remember that these screening tests are purely indicative of more accurate testing. These methods tend to have higher heat losses, higher thermal inertia, which then leads to less accurate energy quantification and exothermic onset temperatures that tend to be shifted to higher temperatures. So more accurate testing is usually required if there's anything concerning, if the decomposition energy is too high, or if there's any low lying exothermic onsets that are close to your process temperature or MTSR, then it's likely recommended to proceed to further more accurate testing. So you can see here we have the differential scanning calorimeter, the Carius tube here, which was designed by AstraZeneca, the Calvit C80, and the TSU unit. So onto the more accurate types of testing we have then. So the adiabatic calorimetry. It's important to know that true adiabaticity refers to a scenario which says absolutely no heat losses to the environment. And in the case of process scale reactors, this means that any heat generated by the reaction is retained within the mixture and not lost to the environment of the vessel itself. Now this is because the ratio between the volume and the surface area of the reaction mass is so large that any heat transferred to the reactor vessel walls is considered negligible when working at these large process scales. So you can see why it's important then to try and replicate these conditions as close as possible at lab scale so that we can obtain the data safely and scale up accordingly. So adiabatic calorimeters like the ARC, which we can see in the top left here, generally utilize a heat weight search method where the oven temperature increases to temperature, holds for a period of time before ramping to the next temperature, usually in 5 to 10 degree increments. So the sample thermocouple can track self-heating of the sample at rate sensitivity of 0.02 degree a minute, so really quite sensitive. And once it detects this self-heating, the oven temperature will then match that sample temperature to track the exotherm adiabatically. Other calorimeters like the VSP2, AOSST, and Phytech can also be used to function in this way, but with the added benefit of having much lower phi factors due to the types of cell construction. So they tend to function pseudo-adiabatically because the heater belt is applied directly to the test cell. It is then subsequently insulated to minimize this heat loss. So these last three tests I mentioned are quite adaptable. It's possible to form additions under agitation, impose back pressures, and we can accurately simulate normal or worst case process scenarios. So these are the sort of tests that are required for when you're trying to determine vent sizes for emergency relief systems. Moving on to reaction calorimetry then. So this sort of calorimetry typically looks at simulating batch or semi-batch processes, and it utilizes heat flow principles between the jacket fluid and the internal reactor temperature. So using these principles, reaction calorimeters can accurately determine the reaction enthalpy, which can then be used to deduce the adiabatic temperature rise and therefore the MTSR. In addition to this, we can take gas flow measurements, determine reagent accumulation. We can get live pH measurements throughout the reaction, and we have the benefit of being able to choose between automated syringe or gravimetric dosing to, make this experiment as close as possible to your process. It's extremely adaptable, and it provides scalable data that can be used to optimize your process, ascertain important plant conditions like cooling capacity and heating power. Moving on then to some more of the thermal stability tests that we have. These three tests simulate the types of drying that you can find in processes. Generally, these three tests are started by estimating the exothermic onset with an initial round thermal scan, about 0.5 degree a minute. We can then see at what temperature these exotherms occur, and we sequentially reduce that temperature, holding these tests isothermally for a 24-hour period to see if that causes the sample to self-heat. So in the top, we have the air over layer tests, simulating thin layer deposits on dryer walls and roofs. We have the bulk powder diffusion test, which replicates drying in base spray dryers and tray dryers. And then we have the aerated powder diffusion cell, which simulates situations where heated air is percolated through a material, so like fluid bed dryers. So the air over layer typically has a 20-degree safety factor, and the powder diffusion cells have a bit of a bigger safety factor of 50 degrees, but still quite accurate. Moving on to more self-heating tests of thermal stability. So we can see here UN test M.4 is determined by exposure of the sample to air at temperatures of 100, 120 and 140 degrees in 25 and 100 mil wire mesh cubes or baskets. So it's also referenced as a basket test, and typically a result is positive and the sample is self-heating when the sample temperature exceeds the oven temperature by 60 degrees over a 24-hour period. Furthermore, we can start to look at self-accelerating decomposition temperatures, especially important for transport. We can use DSC scans of the sample taken before and after thermal stress is applied. If heat flow remains unchanged, like we can see here, then the substance is stable at that temperature. Otherwise, we will then reduce the temperature in 10-degree increments until decomposition behavior remains unchanged. So we can see in this right image here that after a period of 24 hours at 60 degrees, the heat flow of the material has changed, which is cause for concern. It's important to know that adiabatic calorimeters like the ARC can also be used to determine this SADT value. and it works in a very similar way to this method, but in the reverse. So using that methodology I explained earlier, the heat weight search method, increases the temperature rather than decreases the temperature. It's also important to know that initial thermal screening tests, like the DSC, help to determine if a sample is potentially explosive or not, and that's based on the exothermic onset temperature and that energy of that decomposition. So typically, if the energy is greater than 500 joule per gram and less than 500 degrees, it's recommended to pursue further explosive testing. Which brings us on nicely to this slide, explosive testing, where we can see test series 3 of the UN Manual of Tests determines the sensitiveness of substances to mechanical stimuli. So we have the full hammer, which determines whether it's sensitive to impact, and you can see it's consisting of a column with 2 guide rails and a drop weight ranging from 1, 5 and 10 kilogram drop weights, to which is screwed a cylindrical steel striking head. This is then dropped onto the anvil, which contains the impact device holding the sample. By varying the drop weight and height of the drop weight, we can test energies of up to 50 joules. Next to that then, we have the BAM friction test. We have the fixed porcelain peg and a moving porcelain plate. We put about 10 millimeter cubed of sample on this plate, and we can load this peg with up to 10 kilograms of weight via a loading arm. So we can provide a maximum force of 360 newtons. We then move this plate by means of motorized gearing forwards and backwards just once by a distance of 10 millimeters. So both these BAM, full hammer and friction have results consisting of no reaction, decomposition, normally characterized by a change in the color of the sample, or explosion. Generally, each trial in each of these tests consists of 6 attempts, with each trial getting progressively less in terms of frictional load or impact energy. Moving on then, we have the Conan test, which is this piece of equipment here. It uses non-reusable test cells with open orifices, which allows any decomposition gases to escape. We contain this test cell within a steel welded box, and we have propane fueled burners situated on the outside, providing a heating rate to the tube of 3.3 degrees a second. So quite an intense heating rate, and we determine a positive result by characterizing the fragments of the tube post-test. So the more severe the effects are to the tube, the more likely it is to be classed as explosive. So this test is repeated at increasing orifice diameters until 3 negative results are obtained. Moving on to the last test we'll be looking at today, the time pressure test, which consists of a steel cylindrical pressure vessel fitted with a bursting disc situated at the top, which is rated to approximately 2200 kilopascals. We have a pressure transducer, which comes through this sidearm here, and an ignition system, which is comprised of a linen fabric coated with a gunpowder pyrotechnic sort of composition. Again, this test is carried out 3 times, and the result determined positive if a pressure greater than or equal to 2070 kilopascals is reached. So in summary then, we've talked about how testing should be selective and appropriate, that assessments should consider all reasonable eventualities. We talked about the new process considerations and the potential causes of thermal runaway events and scale-up issues. If you have any questions on anything we've covered, please feel free to put it into the question box function, and we'll make sure to collate all of those questions and answer them in a little Q&A document, which we can send to you via email shortly after this presentation. So whilst you're putting your questions in the chat, I'll leave you with this slide here, which lists some of the services we provide at Sigma-HSE, the consultancy, the detailed training courses, and the process safety testing. But if you have any other queries, you can contact our process safety experts in the US by this number or by this email here. And if you fancy it, you can have a look at our website. Thanks for attending. Cheers.
Thank you very much.